All right, so today we're going to continue with chapter 4. We introduced Newton's second law in the last class. And today we're also going to finally talk about the theory of gravity in the Newtonian framework. Just to recap, Newton's first law says, as we now know, highly non-intuitive, that an object will move with constant velocity, that is constant magnitude and direction, unless it is acted on by a non-zero net force. And the word net, again, is important. There could be multiple forces acting on it, but if they all add up to zero, it will still move with constant velocity, which could include the situation where it's at rest, in which case the velocity is zero. And then we had Newton's second law, which is sort of a mathematical formula that quantitatively captures the first law. And again, there is no mathematical derivation for it. It is based on thinking and experimental observation, and then inspiration. And the idea here is that the second law states essentially that if you apply a non-zero net force to an object, then that non-zero net force will be equal to its mass times acceleration. So you can see that it's kind of like the first law, because the acceleration will be zero if the net force on it is zero, which means that if the acceleration is zero, it'll move with constant velocity. Again, no mathematical derivation for this. It's a postulate, and we state it, and then we kind of work with it. I'm going to do a simple problem here, and then after that, we'll switch to the theory of gravity, which is beautiful stuff. Let me switch here to, okay. So in this problem, we are told that there is this boat, and there's a person. So the mass of the boat plus the person all together is 3.5 times 10 to the 2 kilograms, or I guess 350 kilograms. And it has an engine that produces a net horizontal force of 770 newtons. So there's this propeller here. It does its thing. It pushes against the wind or whatever. And then this thing moves forward. And essentially, effectively, this propeller provides a forward force. Technically, it's the air that's pushing, the fan blades is pushing against, the air is pushing back against it. And this thing moves forward with a force of the propeller, which we call F propeller. And that's 770 newtons. Oh, sorry, I take it back. The net force is 770 newtons forward. So you can see in this picture, there's two types of forces acting on the boat. There's the forward force of the propeller, and then there is some resisting force from the water. Between the surface of the water and the boat, there is some sort of, if you will, like a frictional force that is pushing against it. And if you add these two forces together, you get a net force going to the right of 770 newtons. Do you have a question?
Can you just turn it sideways?
Oh, right. Yes. Okay. And of course, there is also, there's a force of gravity down, and then there's the water will be pushing back up. We're going to ignore that because all of that is happening in the vertical direction. And again, F equals ma is a vector equation, and I can think about the x motion separately from the y motion. So we'll just focus on the x motion for now. And so if I were to approach this problem, let's see, what did they ask precisely? They ask in part A, find the acceleration of the airboat, right? So if I were to draw a picture here, let's draw a free body diagram. And I guess we haven't talked about free body diagrams in great detail yet. I will talk about that more in detail a little bit later on. But essentially, a free body diagram is a diagram where you take the object of interest, you isolate it, and you simply draw all the forces acting on it. So in this case, this is the person plus the boat. It has some total mass m, let's say. What do I call it? Do I give it a big M? Little m. And then what we are told is that there is a net force acting to the right. There is a net force acting to the right. So I can call this my positive x, my positive y. So in some sense, this is not even a free body diagram yet because I'm only drawing the net force on it. I'm not drawing all the individual forces acting on it. So, and so what we are told is we want to find the acceleration A given the mass m and the net force in this way. So the mass we're told, remember, is 3.50 times 10 to the 2 kilograms. And then the net force is equal to 7.70 times 10 to the 2 newtons. So this is given to us, this information here is given to us, and we want to find the acceleration. So what do? We're going to apply Newton's second law. Apply Newton's second law. And that says that the sum of all the forces, which is the same as the net force acting on the object, that's what the sum of all the forces means, is equal to the mass times the acceleration. So it's coming to us from the second law. And so therefore, I'm interested in solving for the acceleration. So I'll get A is equal to F net divided by the mass of the boat plus the person together. And so therefore, I can now go ahead here and say the net force is 7.70 times 10 to the 2 newtons. The mass is 3.50 times 10 to the 2 kilograms. You put all that together. What do you get? I'm going to look ahead. You get 2.20 newtons per kilograms. And what are the units of acceleration that we're familiar with? It's meters per second squared. And we can see that newtons per kilogram is the same as meters per second squared, because you can see that a newton, there's a question. Can someone type the attendance code? Does anyone remember it? 7351. So we see here that newtons is the unit of this force, which is the same as the units of kilograms times meters per second squared. So in fact, 1 Newton is defined to be, if you recall, the way we had defined it, 1 Newton was 1 kilogram times meters per second squared, all divided by kilograms. And so you see that this cancels, and you get that the acceleration is 2.20 meters per second squared. Any questions on that? So again, remember that what I'm using here, just to be clear, is that 1 Newton is defined to be 1 kilogram times meters per second squared. That is, if you apply 1 Newton of force to an object of mass 1 kilogram, it will accelerate with 1 meter per second squared. Any questions on that? No problem. Then the other 2 questions are really sort of questions from your previous chapters. So the second question says, starting from rest, how long does it take the boat to reach a speed of 12 meters per second? Why is this like the previous problem? Because now you know the acceleration. So you know that there's some constant acceleration for the boat, and then they're telling you it's starting at rest, and then it's saying how long does it take to reach some speed or something like that. So these are all basically problems from chapter 1. So I'll just kind of quickly go over it. So here is your thing. It says starting from rest, how long does it take to reach a speed of 12 meters per second? We can use this equation V equals V naught plus AT to solve for the time, because now we know V naught is 0, V they tell us is 12 meters per second. And here's the important part, which is that the acceleration was not just given to us, but we actually calculated the acceleration using Newton's second law. So that's what's different in chapter 4. Any questions on that? And then part C is also more like your chapter 1. It says now the engine is turned off after it has reached a speed of 12 meters per second. So now the engine's turned off. What's going to happen is that the boat's going to slow down and then eventually come to a stop. It says that the boat comes to a stop 50 meters after it turns off the engine. And then it says, oh, this is actually an interesting question. It says if the boat comes to a stop in 50 meters after turning off the engine, what must be the resistance force of the water? So it's kind of going along at an initial speed of 12 meters per second, and then eventually it comes to a stop 50 meters later, and that's because there is a resistance force from the water that's causing an acceleration that's causing it to change its velocity and come to a stop. So what is the strategy here is that the first part is just like your physics 1, because you know your initial speed is velocity is 12 meters per second, your final is 0, your initial position you can set to be 0, your final position is 50 meters. And you can use this information to solve for the acceleration, right? Like what must have been the acceleration for it to come to a stop 50 meters later. So I can use this equation again, solve for the acceleration. We know that the final velocity is 0, the initial velocity was 12 meters per second, and then this x minus x naught was 50 meters. And so you get that there's an acceleration of minus 1.44 meters per second squared. And it's negative because the acceleration is pointing, we had declared that this was the positive x direction. And so as the boat is moving to the right, the force of, it's slowing down, which means that the acceleration is in the opposite direction that it's going, and therefore it's in the negative direction. So that's just what you're seeing here, that the acceleration is negative. Any questions on that? And so the final thing that they're asking is what must be the force of the resistance? Well, once the engine is turned off, right, in this case, once the engine is turned off, if you were to now draw the diagram, the force diagram for it, here's your M, there is no longer a force of the propeller. The only force acting on it will be to the left, and that'll just be the force of the resistance. That's it. That's the net force. Again, gravity force and the normal force from the water, they cancel out. So the net force is only the gravitation, this resistance force. So we get that the net force is the same as the magnitude of the net force is the same as the magnitude of the resistance force, which is the same as the magnitude of, I'll put here M times absolute value of A. Because the acceleration came out to be negative, but I'm interested in the magnitude of the force. Or actually, yeah, let me take that out and be consistent. Let's just say it's M times A. So therefore, to find the resistance force, I can just calculate M times A, right? So we just found A as minus 1.44 meters per second squared. We know that the mass of the boat plus the person is 350 kilograms. I multiply these two numbers and I get minus 504 newtons. And the reason you're getting a negative answer is because the resistance force is pointing in the negative x direction. So if they ask you what is the magnitude of the resistance force, then the magnitude is just 504 newtons. The minus sign is telling you that it's pointing in the negative x direction. Any questions on that? So in this problem, part B, they asked us to find the time for something to happen. And we used the result of our acceleration from the previous part. We calculated, and then we went back to our physics, our chapter 2 stuff, and computed this. Here, we first calculate the acceleration using our physics 1 stuff, our chapter 2 stuff, just using the kinematic equations of motion. And once we have the acceleration, I then realized, well, the net force on it is just the resistance force. That must be equal to the mass times acceleration. And so this is the resistance force of the water. So the propeller has to give you a force that is able to overcome that resistance force. Any questions on that? Okay. So let's now switch gears and come to the universal law of gravitation. And so remember that in chapter 2 and 3, we just kind of through experimental observation, we were using the fact that an object in free fall has a downward acceleration of 9.8 meters per second squared. Well, where did that number come from? That number comes from Newton's universal law of gravitation. And we are actually going to be able to derive that number, 9.8 meters per second squared. And it's kind of remarkable. It comes from a combination of the mass of the Earth, the radius of the Earth, and stuff like that. And we will see exactly where that 9.8 comes from. Again, to provide some context, in Newtonian theory, there's the Newton's laws of motion. It will have 3 laws of motion: the first law, the second law, and later on we'll talk about the third law. And now when we talk about the theory of gravity, we're going to have to invoke another law, which is another postulate of how gravity works. Okay, and that is called the universal law of gravitation. And again, Newton was the one that postulated that this is how gravity works based on, he was looking at the way planets moved, he looked at the way things were falling here on Earth, and he then concluded it must be that there is some force of gravity that has a certain form that is explaining all these things that we are seeing. And here is this amazing law. It says that every particle in the universe attracts every other particle with a force that is directly proportional to the product of the masses of the 2 particles, and it is inversely proportional to the square of the distance between them. So that's a lot of words. It actually is simpler if we just write it down as an equation. So this is the equation that Newton wrote down. So he said that here's 2 particles, M1 and M2, and let's say that there's some distance r apart. He postulated that M1 is exerting an attractive force on M2, and M2 in turn is exerting an attractive force on M1. So they're pulling on each other with some gravitational force. And the force is proportional, the magnitude of this force. So this is what this arrow here is denoting the direction of the force that M1 experiences due to the attraction from M2. And this arrow here denotes the direction of the gravitational force that M2 experiences because of the attraction from M1. First off, let's just appreciate how crazy this is. Imagine you're in the 1500s or 1600s, and you go out and you tell people that there is an invisible force. There's nothing here connecting them. There's empty space. But there's this invisible force that it reaches out through empty space and they attract each other with some force. Anything that has mass, any particle in the universe is exerting an attractive force on every other particle in the universe. And the force is proportional to the product of the two masses. So you see that the magnitude of these forces depends on m1 times m2, m1 times m2, and it is inversely proportional to the square of the distance between them. So their distance r apart, so the force goes like 1 over r squared. And then there's this overall constant g, which is like a proportionality constant that we have to then determine from experiment. So I believe, in fact, Newton did not quite know exactly what his own constant was numerically. I think he had some estimate for it, but then after he died, people were able to figure this thing out with more precision. So again, this is the magnitude of the gravitational force, and then the direction of the force on each one of these particles is as shown. And now we know that this gravitational constant, g, has a numerical value that is really, really tiny. It is 6.67 times 10 to the minus 11. And it has these weird units, which you can just check because the left side is newtons, the right side is kilograms squared divided by meters squared. And so you can solve for the units of g, and it will be newtons times meter squared divided by kilogram squared, right? Newtons times meter squared divided by kilogram squared. So that will be, those are the units in SI units for the gravitational constant. Any questions on that? Now take a moment and write this number down. I'm going to give you guys a little top hat question that you will need this number for. So again, this is a very literal statement. Any two particles in the universe are exerting force on each other. So all of us in this room are exerting a gravitational force on each other. The laptop here is exerting a gravitational force on me, and so on. Anything that has mass is exerting a gravitational force. But fortunately for us, this g is a tiny number. Otherwise, it would just be real awkward. It would just be bumping into each other all the time. So let's actually calculate. So the top hat question I'm going to have is, what is the force between two people? Let's say both of them have a mass of 100 kilograms and they're a distance 1 meter apart. See if you can calculate what must be the value of the magnitude of the gravitational force that they are exerting on each other. So let me switch to top hat here. Wait, what is happening with this question? I don't know what is happening there. Okay, so you know the question. Calculate the force between two people. Each has a mass of 100 kilograms. They're 1 meter apart. And see if you can type in your answer. Is it allowing you to answer? It is. Okay, good. I see one person. Type in your answer in units of 10 to the minus 7 newtons. Type in your units, answer in units of 10 to the minus 7 newtons. See if you guys can get that conversion right. 1 meter apart. I was typing this question this morning and it apparently did not go too well. Yeah, put your answer in units of 10 to the minus 7 newtons. Okay, maybe I'll add 15 seconds. The arithmetic should be simple if you're on the right track. If you find yourself dealing with logarithms or something, then you're doing something wrong. All right. Maybe I'll add another 15 seconds, and that's, yeah. Five seconds. All right, let's see what we have. Okay. Yes, so it looks like a lot of you got the right answer. It is 6.67 times 10 to the minus 7 newtons. But if I ask you to give it in units of 10 to the minus 7 newtons, it's actually 6.67. The answer was staring you in the face the whole time. Did anyone notice that?
Yes.
Okay, all right.
Why do you go with E? It would always.
I mean, you can put whatever you want. It's like, it compares it to what I put in as the correct answer. So if I didn't type it as e to the minus 7, that's why I typed it as 6.67, and that's why I asked you to give the answer in units of 10 to the minus 7 newtons.
Oh, my bad.
Yeah, I wasn't just being weird for the sake of being weird.
Oh, so like.
Yeah.
I put 6.67, would that be?
6.67 is correct. I see a lot of people put 6.67 times 10 to the minus 7 or 6.7 times 10 to the minus 7. That's correct, except I think they did not put it in, they put it in units of newtons rather than 10 to the minus 7 newtons. So, and then some other people put 0.00067. So that's also correct. The second last one here, if it's 7 decimals over, and so on. So the point is that the gravitational force that two people exert on each other if they're 1 meter apart, they're 100 kilograms each, is 6.67 times 10 to the minus 7 newtons. 10 to the minus 7 newtons is a very small force. And that's why we are not irritated all the time. We barely feel the force. However, we feel a very strong gravitational force from the Earth. And why is that? Because in our calculation so far, what we did, well, I should actually say, right, maybe it's worth going through this calculation here very quickly. The question that I just did is, well, it's G, and then these two are 100 kilograms each. And then basically this is just 1 meter squared. So the denominator is just 1. And then up here, I just have 10 to the 4. 100 times 100 is 10,000 or 10 to the 4. So then you just get G, which is 6.67 times 10 to the minus 11. And then you have here times 10 to the 4 in the end newtons. And so 10 to the minus 11 times 10 to the minus 4 is 10 to the minus 7 newtons, like that. So in some sense, the arithmetic was kind of simple because this is just 1, and you just take the 10 to the minus 11, multiply by 10 to the minus 4, and then you get 10 to the minus 7. So that's a very, very tiny force between two people. But now the reason we are all stuck with the Earth is because we just computed the force between 200 kilogram people. But now with the Earth, a person would be 100 kilograms, but the Earth would be, I think it's 6 times 10 to the 24 kilograms, right? 6 trillion kilograms. So because the Earth has a huge mass, it is able to overcome this small gravitational constant. And I should also point out that this R here is the distance between the centers of the two objects. So when we compute the force that Earth is exerting on us, this R here will be like the radius of the Earth. but the mass is still really, really big, so that even though the radius of the Earth is big, you're still able to overcome this g, and that's why we're all stuck to the Earth. So if I were to apply this formula between the Earth and a person, so here's the Earth, and then here's a person on top. This has a mass m, the Earth has a mass me. The distance between their centers is the radius of the Earth, essentially. And so then you see it's g times m1, m2 over the distance between them squared. And if I now plug in, so everyone agree this is the force from gravity. What we can now do is we can ask, what is the acceleration that we would experience under this force? So let's say like you're like 1 meter above the ground. That's the distance between you and the center of this is still basically the radius of the Earth, right? It's the radius of the Earth plus 1 meter, but we can ignore that 1 meter. So if you're 1 meter above the ground, what acceleration will you feel? Well, it's going to be this gravitational force that's acting on you divided by your mass. That's going to be the acceleration that you feel. So Newton's second law says that, let's imagine that there's some object here just above the surface of the Earth. The net force on this object is the force of gravity acting downward. That is the only force acting on this object in free fall. And so therefore, that force is the force of gravity. That net force has to equal its mass times acceleration. Any questions on that? So what is the acceleration? I'll just divide both sides by the mass. So this m cancels out. And therefore I get that the acceleration is the gravitational constant times the mass of the Earth divided by the radius of the Earth squared. That is the acceleration that you will feel if you're in free fall just above the surface of the Earth. And notice that this acceleration is just determined by a bunch of constants, right? You can go to Google, look up the mass of the Earth, look up the radius of the Earth, and we know the value of the gravitational constant. That's going to give you some number. We give this combination a symbol, we call it G. And if you plug in the numbers here, what you will find is that this is 9.80 meters per second squared. That is where that number comes from. Any questions on that? Again, let's step back and appreciate how amazing this is. Experimentally, people found that everything was falling with 9.8 meters per second squared. No matter what you dropped, and you can see why that is, because the m here cancels out. This m and this m drop out in this acceleration. So you see that the acceleration of any object in free fall doesn't depend on its mass. It only depends on the gravitational constant, the mass of the Earth, and the radius of the Earth. It doesn't depend whether this is a hammer or a feather. It doesn't matter. They will fall at the same rate, 9.8 meters per second squared. And this is what's weird about gravity, is that the force you experience due to gravity is proportional to your mass. And by Newton's second law, the net force you experience is also proportional to your mass. And so therefore the masses cancel out and your acceleration is the same whether you're a hammer or a feather. It doesn't matter. This is not true of any other force. If you look at like an electrical force between, say, a proton and an electron or something, the electrical force doesn't depend on the mass of objects. It depends on their electric charges. Okay. And so therefore the acceleration they experience will be different. A proton and an electron will accelerate at different rates in an electric field as opposed to a gravitational field. So there it is. That is the number 9.8 meters per second squared. You can also then use this idea and figure out what must be the acceleration of free fall if you're on the surface of the moon. Well, we apply the universal law of gravitation. It is g times the mass of the moon times the mass of the person divided by the radius of the moon squared. That has to equal the mass times acceleration. That is the net force on the surface of the moon. The m cancels out. And now we can understand that, if you now look up the numbers for the mass of the moon and the radius of the moon, you calculate this number, you get 1.62 meters per second squared. So because the mass of the moon is much smaller than the mass of the Earth, you experience a smaller gravitational acceleration, which is why those astronauts were able to kind of bounce around and kind of semi-float, and they could hit a golf ball really far. That actually happened, right? They actually hit a golf ball on the moon. And that's because the acceleration due to gravity is very small. Okay. So this is the 9.8 on the surface of the Earth, 1.62 on the surface of the moon. This is why the hammer and the feather fell at the same rate in the absence of air resistance in that video I showed you guys earlier. And you also saw that they kind of fell more gently than they would on Earth. And that's because on the moon, they're falling with 1.62 meters per second squared of acceleration instead of 9.8. There's that picture. Finally, let me introduce the concept of weight. So when we say what is the weight of, or something weighs something, what does that actually mean? What it actually means is what is the gravitational force due to the Earth on that object, or due to whatever planet it's on, right? So when we say that something has a certain weight, what we're saying is what is the gravitational force on it. So weight in SI units has units of newtons. It's not kilograms. Kilograms is referring to mass. Weight is referring to newtons. And in the US customary system or whatever, force is measured in pounds. And that's why we talk about people weigh so many pounds. What that means is that is the amount of gravitational force being exerted on them in US customary units. So the weight of an object is again equal to the gravitational force, which is g times the mass of the Earth times the mass of the person divided by their distance squared. But this combination here, remember, we're giving it a name, we're calling it g. Let me write out here. The force due to gravity is g m1 m2 over r squared. So the force you experienced as a person is g times your mass times the mass of the Earth divided by the radius of the Earth squared. This whole thing here has the value of 9.8. So therefore your weight is just your mass times 9.8. Any questions on that? And on the surface of the moon, it'll be your mass times the g on the moon, which is 1.62 meters per second squared. Let me do one quick top hat, which is see if you can calculate the mass of a 100 kilogram person on the surface of the Earth. Hopefully I didn't mess up this question too bad. Okay. I don't know what happened this morning. Yeah, the answer is 980, right? 9.80 meters per second squared times 100 kilograms. So a person that weighs, that has a mass of 100 kilograms experiences a force of 980 newtons due to the Earth, as opposed to 6.67 times 10 to the minus 7 newtons from another person that's also 100 kilograms. All right. So yeah, go ahead and answer this question and then we can end for today. I guess I gave you the answers for both questions today. Anyway. 100 kilograms. I'm just using 100 kilograms because it's an easy number. right, I will see you guys on Friday.